Okay, hello everybody. I've been looking forward to doing lectures on this topic for quite some time, and so it's feeling quite good to finally get this stuff out there. I want to talk, and I think it'll probably break up in several parts, but I want to talk about the history of confusion and paradoxes and paradigm shifts in mathematics. And so mathematics hasn't just had a kind of smooth, constant upward development. It's more like a kind of the kind of punctuated equilibria concept one finds in biology, where mathematical theories will stay static for quite a while, and then suddenly some big breakthrough idea causes a great sort of revolution. And as far back as we look, there have been questions in mathematics or issues which just don't seem to make sense. And these still exist today. And in fact, these kind of mystery spots are often the places which end up yielding the most important mathematical and indeed technological insights. So we're going to start off in ancient Greece with Pythagoras, and we're going to try and follow a somewhat chronological tale about how people developed things like group theory and set theory and ideas about infinity, and then how people struggled to axiomatize it all and make it fit in with the age. And we're going to show how that wasn't even possible. And we're going to look at how this sort of demonstration that mathematics couldn't be confined and understood in some funny way really led to the birth of the computer. Okay, so we're going to start off with the ancient Greeks, with Pythagoras, who inspired a lot of people to study mathematics with his notions that all of the things around in the world could be understood through numbers. He was born around 570 BC, and he's probably most famous for his Pythagorean theorem about the triangle. That if you have a right angle triangle, then the square of one of the flat sides plus the square of the other right angled side equals the square of the hypotenuse side between them. However, Pythagoras also developed theories about many other things in mathematics and in nature. For example, he observed how the harmonics in music can be represented by fractions, as in one whole number or integer divided by another one, and how the orbits of planets, similarly, one could understand them through these ratios. In fact, wherever Pythagoras looked, it seemed as though numbers, or what we call rational numbers, which is one whole number or integer divided by another one, can be used to understand what's going on. Okay, so the problem arose from one of the followers of Pythagoras' teachings, whose name was Hippasus, and he did some very interesting mathematical work which was appreciated by the Pythagoreans. However, he did something which was very much not appreciated. He found a number which could not be expressed as a rational number. I mean, it's now called an irrational number. The very roots of these words, rational and irrational, as we understand them today, implies that this number that he discovered in some sense does not make sense. What is this, a rational number? Well, today we would call it the square root of 2. And it's very easy to construct in a sense. Take a square, which is 1 unit by 1 unit, and measure the distance from one diagonal point to the opposite diagonal point. That number should be about the square root of 2. In fact, Pythagoras' own theorem infers this. So, what's the problem? Well, the Pythagorean view was that all of these things could be understood in terms of rational numbers. An integer divided by an integer. But what Hippasus showed was that, in fact, the square root of 2 could not be represented as one number divided by another number. And just in case you think that this is some kind of historical curiosity or kind of backroad of mathematics which has no influence upon today, well, even today people are not really sure if the square root of 2 is a number or not. No one's found any sort of pattern in the number. There's no way to sort of really work with it in a proper way. It's still sort of a kind of thorn in the side of mathematicians who would wish for the subject to be a lot less confusing, essentially. Anyway, how does one prove that the square root of 2 is not a rational number? Well, there's a nice little proof of it. I'll go through it now. Okay, so in order to show you why the square root of 2 is not a rational number, I'm going to use what's sometimes called a reductio absurdum, or proof by contradiction argument. We're going to start by assuming that the square root of 2 is a rational number, and then we're going to show that that leads to nonsense. So we'll assume that the square root of 2 is a rational number. That means it can be written as one integer divided by another integer. And so now we have to introduce this idea of irreducible fractions. So consider the fraction 10 divided by 5. Well, that fraction can be reduced because 10 is equal to 2 times 5 and 5 is equal to 1 times 5. So we can sort of cross off the 5 off the top and the bottom of that fraction, and we get a half, which is an irreducible fraction. So an irreducible fraction is where the numerator, I think that's the top part of a fraction, and the denominator have no factors in common. And we can always reduce our fractions down to this kind of form. So if the square root of 2 is indeed a rational number, then we should be able to write it a divided by b, where a and b don't have any factors in common. So then we have this equation. A divided by b is equal to the square root of 2. Well, we don't know much about the square root of 2. All that we really know is that if we square it, we get 2. So this equation can be transformed into a squared divided by b squared equals 2. And so we can rearrange that to say that a squared equals 2b squared. And so now we know that a has to be an even number. How do we know that? Well, we know that it's written as 2 times b squared. And so it's 2 times some integer, so it must be even. A squared must be even. And if something squared is even, then that thing which is squared must also be even. I mean, 16 is even implies 4 is even, for example. So we know a is even, so we can write a as 2 times k for some integer k. So now, substituting this back into our old formula, a squared equals 2b squared, we get that 2b squared is equal to 4k squared. And so now, interestingly, we get that b squared is equal to 2k squared. So the square of this number b is also an even number. So a and b are both even numbers. But we said we started with an irreducible fraction. We said we're going to cross off any factors that a and b have in common. And yet we've now just shown that they're both even. So a divided by b is not an irreducible fraction. So our initial premise has been contradicted. So this existence of a contradiction implies that the square root of 2 is not a rational number. Now, I think it's very elegant actually, and quite worth sort of going through this argument if these kind of things interest you. I think it's a lovely idea, this proof by contradiction. I think it was Hardy that said that the chess player would only offer a piece or a queen as a gambit, whereas the mathematician offers the whole game. When they try to do one of these proof by contradictions, they set it all upon the line and they hope that a contradiction comes out. Anyway, much as this was a lovely piece of work, and I'm sure Hippasus was very proud of himself for discovering this, it didn't lead him to the best of futures, because in fact, when his Pythagorean friends found out about this, he was thrown overseas and killed. I think the history is a little unclear, but it seems as though he was basically murdered because people did not want the thing that he discovered to be well known, because it completely undermined their worldview that everything can be expressed as these kind of ratios, these lovely harmonic things of one number divided by another number. And so he was shut up for a while, and I suppose it took quite a long time for these issues with the square root of 2 to really resurface. But they have, and even nowadays in the computational age, people are starting again to get quite anxious about this idea of the square root of 2. I mean, there's different branches of mathematics, and I think it's quite a good thing that mathematicians have formed into sort of different groups who use different kinds of belief systems. They know what their beliefs are, so they don't have to argue with each other. For example, an algebraicist might say, well, it's okay to introduce a number which we'll call the square root of 2 into our number system, and it satisfies all the laws of arithmetic and we can work with it, and that's great. However, someone who's actually interested in like representing numbers and doing proper calculations with numbers would not be so happy with the square root of 2. Let me show you a decimal expansion of the square root of 2. Here it is. These are the first few digits of it. Looks kind of random, right? Well, maybe we're looking at it in the wrong way. Perhaps if we look at it in binary, I mean, it is related to the number 2 after all. So here it is in binary. There doesn't seem to be much of a pattern here. Well, this is the thing about the square root of 2. We can use our computers to work out this number up to a finite length, but we can never really know what the square root of 2 is. In fact, it's just physically impossible. There's not enough time, there's not big enough computers, there's not enough attention span in the human head. We can never know what this number actually is in completion. We can get nice formulas for it to compute it, but ultimately it escapes us. Okay then, so I'm going to skip quite far forwards now. There are other sort of sources of confusion in mathematics which I could mention. Things like how people couldn't trisect an angle. People tried for a long time using the geometry which Euclid developed, another fantastic Greek mathematician, and they spent a long time trying to use his methods to trisect an angle. So using ruler and compass, can you find a surefire way of cutting an angle into 3 equal angles? And people tried this for a long time, and it was a source of confusion, but it turned out that it just couldn't be done. It was just impossible to do it with straight line and compass. So yes, that was a source of confusion, but I'm trying to talk about the sources of confusion which are still sort of echoing in the corridors of maths departments today. And so the next one I want to talk about is something which was discussed by Galileo in round about the 1600s. So he was thinking about the idea of infinity, and he discovered a rather interesting sort of paradox in a way. It goes like this. Think about a circle. Now, we can approximate a circle by a polygon with a regular polygon with a very large number of sides. So we can approximate it as a square. A little better approximation would be a pentagon or a hexagon or an octagon. The more sides we have on our polygon, the closer we get to approximating the circle. So Galileo proposed, well, we could imagine a polygon which has a very large, or let's say infinite number of sides. Now, I think this may have been where he went wrong, because, I mean, does the word infinite actually mean anything? It just means non-stopping. I mean, is that a number? Anyway, so he suggested that we could consider this circle with an infinite number of sides, and then what he did, which was very clever, was he drew another circle around the outside of the first one. And he said, look, if we draw all these lines out from the middle of the first circle, one through each of the infinite number of corners of this polygon that this inner circle is made of, look at these lines. They diverge. So there's not enough lines to go through all the points of the bigger circle. So you have one infinity which is sort of big enough to cover the smaller circle, but you need an even bigger infinity to cover the larger circle. And there were many other kinds of paradoxes and things which, well, supposed paradoxes which crop up when you start thinking about infinite things. For example, are there more even numbers than there are whole numbers? Well, in some sense you'd say, well, okay, half the numbers are even, so there should be half as many. But in another sense you can say, well, if we get any number and double it, sorry, if we get any even number and half it, we get an integer. So one can see from both sides that in fact perhaps there are the same amount of whole numbers as even numbers. Excuse me for speaking in kind of, I know some of my terminology is not exactly correct. I'm trying to simplify things down a bit here. Okay, so I'm just about to get on to the discussion of one of my favourite mathematicians of all time, who I think probably did more than anyone else to introduce confusion into mathematics, as well as really moving the whole area in a completely different direction to, I think he really had a great impact on the sort of area, the direction that mathematics went in. But before I discuss him, I'd like to say something about somebody else. Somebody who didn't live as long. Somebody who actually died at the age of 21 in a duel with somebody. His name was Galois, and this young man was known to have a fiery temper, and he ended up getting into a duel with somebody, and so people say, on the evening before the duel, he feverishly worked out and wrote down as much of his theory as he could. Galois theory. Galois theory is a theory in abstract algebra. So it's really a kind of connection between two areas of mathematics, one called field theory and the other called group theory. And Galois theory actually did a lot to reduce confusion in mathematics in some ways. For example, using this theory and building on it quite a lot, it was eventually possible to prove that you could not trisect an angle via Euclid's methods. However, as I shall discuss later, the kind of explorations, especially in group theory, which Galois' sort of abstract algebra approach motivated, led to the discovery of some some things which people don't really understand at the moment. I'll talk about those later. Anyway, on to the discussion of one of my favourite mathematicians, Gregory Cantor. And so Cantor is an absolutely fascinating character in my opinion. He grew up in a rather religious background, and apparently his father instilled in him quite a lot of idea that he would go on to do something great. And he basically got very interested in mathematics, and he considered his work to be sort of for the glory of God in some sense. I'm not sure how. I think maybe he wasn't so Christianly orientated, but he certainly believed in a divine being, and he believed that by trying to understand infinity, he could sort of get closer to God, I imagine. I mean, who knows what was going on inside this man's head, but one thing's for sure, he created some of the most radical theories and really started to untangle this idea of infinity, which is just so full of paradoxes. For example, the thing I was just talking about to do with Galileo and the circle. In a way, Cantor sort of resolved that paradox by his work. And there's some lovely quotes about Cantor. He was called a corrupter of youth, a renegade, a scientific charlatan. His old friend said of him that his work was a disease from which he hoped future generations would recover. And there are many mathematicians even today who basically consider Cantor to be the one who polluted mathematics and turned it from something concrete and computational into something sort of wishy-washy and abstract. So, I mean, this guy provoked a lot of reactions, and that's because his theories couldn't be easily disproved, and they were absolutely radical. He asked the question, is the amount, or cardinality as he would like to say, but I'd rather keep terminology to a minimal, but he'd say, is the amount of even numbers equal to the amount of numbers? Or is the amount of integers equal to the amount of pairs of integers. So, for example, if you imagine a line with the numbers 1, 2, 3, 4 going off into infinity, and if you imagine a grid where every point is labelled by coordinates, like 5 across, 2 up, etc., of the number of points on the line equal to the number of points on the grid. These are really baffling questions. And Cantor came up with a fantastic way of trying to answer this. He said, well, if we can put two sets into one-to-one correspondence with each other, then they must have the same number of elements within each. For example, if you have a cinema, it will have a certain number of seats. And if you have one person sat in every seat and no one without a seat, then you know automatically that the number of people sitting in the cinema is equal to the number of seats. You don't need to know how many seats there are. And similarly with numbers. I mean, if you take all of the numbers and multiply them by 2, you get all of the even numbers. So that gives you a one-to-one correspondence between the numbers and the even numbers. So I'll call it their cardinality, the sort of amount of them that there are, is the same. So, although the number of integers is infinite, it's the same infinity as the number of even numbers, or the number of odd numbers, or the number of numbers divisible by 3. In fact, this early part of Cantor's work really sort of starts to imply that there's just one infinity. But actually, it gets much more interesting than that. But before I go on, let's talk about this problem of the grid. We have a grid of points, that's two-dimensional space. So surely there must be more points in this 2D grid than there are in this 1D line. Well, no. Why? Because if we take this kind of snaking path here, going upwards and downwards in diagonals, we can put the points of the grid in one-to-one correspondence with the points of the line. So the cardinality of these two sets are the same. So from now it starts to look as if, okay, there's this thing called infinity, and it describes lots and lots of these sets which are too big for us to think about. But then Cantor discovered something truly remarkable. And I mean, Cantor was a manic depressive. It's probably his episodes of mania gave him the sort of, well, helped him to discover some of these amazing results, and also tragically messed up the last part of his life. But I can only imagine how he felt after he proved this next result I'm going to talk about. I would be sure it must have been during one of his manic episodes when he came up with this argument why there were some infinities which were bigger than other infinities. So let me explain. Okay, so somewhere between the time when Pythagoras was thinking that all numbers could be expressed as a kind of fraction or rational number, and the time of Cantor, a guy called Stevin introduced basically what is now our modern decimal system. The idea that you can have a certain integer, like say 3, and then you put a decimal point, and then you can have lots of other numbers representing how many tenths do you have, how many hundredths do you have, how many thousandths do you have, etc. So 3.141592, etc. And Steven introduced this concept, and it was really, really well taken aboard because it made calculations much, much easier. But it also sort of sank into the minds of mathematicians, of course, and people started to think of things like pi as 3 followed by some infinite string, 3 point, and then some infinite string of symbols from 0 to 9, and similarly with square root of 2. And this really opened the door for what are now called irrational numbers. So the square root of 2 was the first known irrational number, basically given its label as a sort of punishment because people thought it didn't make sense. But after Steven's sort of introduction of this system, people started to think, well, if we can always put as many extra decimal places onto any number we like, we can have a continuum where even between two rational numbers, we can find any irrational number. We can really, really make loads of new numbers up, which could not be written as the fraction of one number divided by another. So this is really a sort of fantasy in a way, because no one can actually do this, but people imagined it to be so. And basically, what Cantor did is he showed that, well, what was called the real numbers, basically people started to think of the set of real numbers as the set of rational numbers in union with a set of irrational numbers. So it was all the numbers that you can write as fractions, like a third or 3/2 or whatever, plus things like pi and the square root of 2, and also plus all these other extra numbers which are kind of hard to talk about really, but they're things that you can form by getting an integer and putting a decimal point and putting loads and loads of numbers after that. And so this conception of the continuum started to emerge. And then people started to wonder, well, are there more points in this continuum? Are there more real numbers than there are integers? Put more simply, it shows that there are more numbers. Well, the simplest way I can put it is there are more real numbers between 0 and 1 than there are integers. It's not just that they're the same kind of infinity. The infinity which describes the cardinality of integers is less, significantly less than the infinity which describes how many points there are between 0 and 1. And how do you show this? How on earth do you prove something like that? Well, his wonderful idea was, let's do a proof by contradiction. Let's imagine that we can list all of the numbers from between 0 and 1 in one big long list. And it doesn't really matter how you do it. You could do it completely randomly. So say the first number on the list was 0.862900000, blah, 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 blah. And the second number on the list was this, and so forth. And so this is a list that goes on forever. And so it has the same cardinality, the same kind of size as the set of integers. But Cantor said this list cannot contain all of the real numbers. Well, why ever not? Well, because we can make a number which is not in the list. Okay, how do we do that? Well, let's create such a number. We'll look at the first entry on this list. And let's say that's a 3. Well, then we'll change it into a 4. We'll look at the second entry on this list. Let's say that's a 7. We'll change it into an 8. We'll look at the next entry on this list. Let's say it's a 9. We'll change it into a 0. And so forth. You alter the value of the sort of diagonals all the way along this list. So then if you take those kind of messed up, those kind of altered diagonals, and you string all those together to make a number, then there's no way that that number can be on the list. Why not? Well, could it be the first value on the list? Well, no, because it, by definition, has a different first entry to the first entry on the list. Could it be the second entry on the list? Nope. We change the second entry. Could it be the nth entry on the list? Nope, because the nth value of this number is not equal to the nth value across of the nth value in our list. This new sort of number is nowhere upon our list. So the existence of it contradicts the assumption that the number of reals is equal to the number of rationals. So there you go. Cantor proved that there are some infinities which are bigger than others. And he went even further than that. I mean, he proved that if you have any set, if you take the collection of all subsets of that set, then you get something bigger. A subset is just a set contained within a set. For example, a set of monkeys is contained within a set of mammals. But Cantor showed that this was also true for infinite sets. So we start with the integers. They're the sort of smallest infinite set we know of. We take the set of all subsets of integers and we get a bigger infinite set, which turns out actually to be equal in size to the equal in cardinality to the set of reals. But then we can take the set of all subsets of reals, we get an even bigger infinity. Oh, we can carry on doing this forever. We have an infinite sequence of infinities getting bigger and bigger and bigger. Infinities so big that we couldn't even give them names, and they go on and on and on forever. Remarkable. Now, people have been very wary about talking about infinity for a long time before Cantor came along, and his papers were met with quite a lot of criticism and simple ignorance. In fact, it was really, I don't think he really saw the sort of great praise which his theories got before he died in an insane asylum. I mean, he was manic depressive and he had some bad things going on later on. He did all these wonderful theories, but people didn't seem to appreciate them. And then he had some family problems, and the guy just had a mental breakdown. But I mean, there are people who do think that Gregory Cantor's work was a very corrupting force upon mathematics. And I can somewhat sympathise with that, because it has made mathematics a much less constructive subject. And personally, I much prefer working on areas like graph theory or number theory, where you really know what you're dealing with. The bits are the bits. Whereas Cantor's findings push people towards more abstract subjects like topology and sort of high-flying set theory. However, I mean, basically, I think it's fantastic that those doors have been opened up, and it just gives people more opportunities to study these things. And it's kind of sad that people have this animosity towards Cantor when basically all he did was say, hey, there's a load of extra stuff you can study. I mean, it's not like anyone's putting a gun to anyone's head. But certainly, the other thing that people hated about Cantor's theories was it just opened up a massive can of worms of contradictions. You see, he based all his ideas on a lot of his ideas on set theory. This idea of being able to put things in one-to-one correspondence with each other. It's a set theoretic concept. But then you start thinking about infinite sets and it starts to get quite confusing. I'll give you a few different paradoxes which crop up. What about the set of everything? Can we consider a set of everything? Absolutely everything. Well, one of Cantor's theories says that given any set, the set of all subsets of that set has a larger cardinality, it's bigger. So if you think you have a set of everything, well, what about the set of all subsets of everything? That's bigger. It's sort of contradiction.